I guess we can start. Thank you for coming. And today we are going to have two speakers from the same group, and the group is strange and flat quantum materials. And the first speaker is Ivo Gabrovski, the new PhD student of this group, and the second speaker is Louk Rademaker, the new professor of University of Geneva. And today we are going to talk about quantum materials, and Louk's presentation is going to be about 2D materials and 3D materials made by the same atoms. And Ivo is going to make a small introduction into band theory and some basic ideas of quantum matter. So Ivo, the floor is yours.
Thank you, Anna. Yeah, so I'm going to try in 15 minutes to, well, first of all, tell you why it's really nice to know about electrons in matter, and then also what is the most common way to describe them. So I guess for many of you this will be nothing new, but I hope that at least some of you might learn something new. So, a good question to ask, of course, is why do we even care about electrons in solids? And as it turns out, this is not only some issue concerning condensed matter theory wackos like again in this picture, because well, electrons, they turn out to determine almost every important property in a material. So starting from mechanical properties, so electrons form bonds in the material, so of course they're going to influence the mechanical properties. Electrons can carry energy, so they're going to also influence thermodynamic properties. Well, this one, I guess, doesn't surprise anybody, but electrons also determine the electronic properties of a material, and they also do the optical properties, because after all, light is just electromagnetic wave, so it interacts with matter through the charges in the matter, and well, electrons are clearly charged particles, so light interacts with electrons in matter. So if we know the electronic properties, we can usually also infer the optical properties. So magnetic properties are also consequence of electrons, as well, magnetism stems from the intrinsic angular momentum of electrons, but I guess we won't focus on that today. So, if electrons are so cool, then how do we describe them? Well, they're quantum particles, so of course we're going to use the Schrödinger equation, where this psi now is the electron wave function, and this V is the potential. So, for example, if we have a free electron where the potential is 0, our solution for the wave function is going to be a plane wave. However, if we now put our electron in a crystal, this means that the potential is going to be a periodic function. It's going to be periodic from unit lattice to from unit cell to unit cell, and therefore we can also expect that the electron density is going to be periodic in the lattice. And from there, we can infer that our wave function is going to have this form, and we call it a Bloch wave function. So that's two parts. So this one is the periodic part. It's periodic in the in real space, and this part is the same as what we had for the free electron, and it's a sort of plane wave. So if we have this lattice in one dimension, and this black is sort of what we would expect for some wave function. Right. So next step, we want to know the energy of the electron. As we normally do in physics, we want to know the energy of things. So we can start again with the free electron, which has a very simple expression for its energy, which is the same as the kinetic energy of the classical particle. But now, if you want to move to an electron in a crystal, things become very complicated very fast. Because if you want to have a full solution, we want to take into account the potential, and these potentials, they usually have quite complicated expressions, and even in the most simplified form, they're still quite complicated to solve exactly. So instead, what I'm going to offer you today is a sort of hand-wavy solution, which is not very physical, but I think it gives a lot of physical insight into how how the energy is going to behave. So what we're going to do is we're going to say, let's say that our electron is nearly free, which means that we're going to say that its wave function is approximately the wave function of a free electron. but what we're going to do is we're going to keep the periodicity in momentum space. So from minus pi over a to pi over a, we're going to have the Brillouin zone. And if we take now these states at the edge of the Brillouin zone, we can combine them to form standing waves, which are going to be a physical representation of the time-independent solution for an electron. So if we now have this sort of potential, so the potential drops around the ions, and we take the standing wave solutions and we plot them, we're going to see that one standing wave is going to pile charge on the positively charged ions, and the other one is going to pile charge away from the ions. So clearly, in the first case, we're going to have a lower Coulomb energy, which means that this state in general is going to have a lower energy. So if we now go back to our diagram of energy versus momentum, what we expect is going to happen at the edges of the Brillouin zone is that a gap is going to open. And then we're going to have one band which is below this gap and a second band which is above this gap, but between them we don't have any physical states. So in fact we can keep on doing this for every integer multiple of pi over a, and if we do that, and if we do that, we're going to see again gaps for every integer. And in principle, we can have this full information for the system from this picture, but it's a little bit annoying to have such a large x-axis. So what we can do is we can remember that we have periodicity in momentum space, so that this point is related to this point in momentum space, and we can now sort of start folding this full extended scheme to obtain this reduced scheme that is on the bottom. And this is what is generally understood when people say a band diagram. So, of course, this is a very simplified model in one dimension, and even though it still retains some important properties like having band gaps, if you want to move to a more real picture, we're going to need to put a lot more effort. So, how does a real band diagram look like? It looks like this for silicon in this particular case. So it has a base-centered cubic structure in real space, which means that its Brillouin zone is going to look like so. So when I was a bachelor student, I found all this very confusing. Also, in one dimension, we managed to plot, well, we can plot momentum on one axis, but then we move to 3 dimensions. It's a bit hard to plot on one axis all momentum. So instead, what is done is, well, people usually say that we have certain points of interest in the Brillouin zone, so-called high symmetry points, which are denoted with letters, and we can expect that all of the interesting physics is going to happen on these points. So we just plot these points and the lines connecting them in momentum space on one axis. So for example, if I go along this line, in the Brillouin zone, this means going from this L to U to W and then to gamma. So one thing that you noticed also probably is that in silicon, unlike the previous example, the band diagram looks much more complicated. And there's many reasons for that. So first of all, this is a real crystal in 3 dimensions. So it has certain structure in the unit cell. It has certain electronic orbitals which combine in different ways, which means that well, the way in which this charge may pile up in certain places of the unit cell is not so trivial anymore. And in fact, what people do and what this guy has done for this particular graph is use numerical calculations. And well, if you're a quantum club fan, you might recognize this band diagram because it's also in the background of the quantum club, as was pointed out to me by Louk a few days ago. So we talked about how we can construct these bands, but now it's time to also fill them with electrons. And as you might know, electrons are fermions, which means that they only one of them can occupy a given state. And so if we now take the occupation number of electrons as a function of energy at 0 temperature, which is this blue line, what we're going to see is, well, the system wants to be in the lowest possible energy state. All electrons want to be at the lowest possible energy, but only one of them can be in the lowest possible energy, and all the others, they pile up at higher energies. And the last electron that comes last in this picture is going to have energy EF, which we call a Fermi energy. So, and this is for 0 temperature. When we increase the temperature, we have higher energy states thermally accessible, and this curve will start to smoothen out as we increase the temperature. So, coming back to our band diagram, what this means is, well, in this case, the Fermi energy is at the 0, which means that all bands below this energy are going to be fully occupied, and all bands above here are going to be completely empty at sufficiently low temperatures. And something that an immediate consequence of this is that, for example, we can know that silicon at sufficiently low temperatures is going to be an insulator. Why? Because if you want to generate a certain electric current, we need to have a sort of net movement of electrons in a given direction, which means that we have a larger population at a certain momentum. And so if I want to maybe take this electron from here and put it at a different momentum so that I can have a current, this is virtually impossible because all the other states are taken, they're occupied. So this is also what sort of defines an insulator when we talk about band theory. An insulator is just a material where this Fermi energy lies in the band gap. And in particular, for silicon, we say it's a semiconductor because its band gap is very small. And as we increase the temperature, and you will see in here, these states can easily become occupied. And conversely, well, what is a metal? A metal is a material where this Fermi energy lies somewhere in the band, so that it costs virtually no energy to put an electron in a different momentum state and have a current. All right. So as I said, as we increase the temperature and this occupation sort of smoothens out, we're going to find ourselves in a situation where these bands above are going to start being occupied, and therefore this whole picture is going to start being conductive. In fact, this is a general property of insulators and semiconductors, that if we increase the temperature, well, the conductivity grows and the resistivity drops. So this is one way in which we can sort of externally control the occupation very easily with temperature. Another way in which we can control the occupation is by modifying the Fermi energy. So the Fermi energy is always some function of the electron density, because as you can imagine, if we just add more and more electrons in the system, they're going to occupy higher and higher energy levels because of the Pauli exclusion principle. And so in silicon, if we inject it with more electrons, we can effectively move the Fermi level. And this is known as doping. So what else can we get from the band structure? Well, as I explained already, or tried to explain, just by looking at the band diagram, you can already understand a lot of physics, the basic conductivity properties, and also, in general, it's a nice picture of where electrons sit at, and what is their energy at given momentum. But also from the band diagram and the band structure, we can, in principle, find the excitation energies. So if I want to excite an electron, maybe with light, and have it jump from here to here, or here to here with some momentum difference, well, I can essentially find the sort of excitation spectrum. Another thing that I can always calculate is, well, the group velocity of the electron, which is going to tell me something about how the electron moves. And I can also, from the band structure, infer the effective mass of the electron, because as it turns out in crystals, where the electron is not free, and as it moves, it interacts with the local potential, it can behave as if it has a larger mass than it actually does. In fact, it cannot, and sometimes this mass is significantly larger, and looking at the effective mass can sometimes result in some interesting physics. So I would like to leave you with that, and now it's time for Louk to tell us a little bit about carbon and why it is so special, also in the framework of what I just explained to you. So, if you have any questions.
I realized I can left a piece of carbon.
So, if you have any questions to Ivo, it's a very right moment to ask.
Everybody knows band theory.
Or if you have questions, you can also ask him during the admiral.
Thanks, Ivo, for that wonderful introduction. I had to quickly run out because I forgot a piece of carbon. And just as a little bit of fun background, you might remember over the summer there was a lot of talk about room temperature superconductivity was discovered. You guys remember that? So turns out that it was all bullshit, but one of the things that really made it very popular was this video online saying, look, if I put it here, it levitates. So it looked exactly like this. You see, I move it a bit and it stays where it is. It's completely levitating. So that's a sign that's a room temperature superconductor. And that already was like, come on, guys. You don't need a room temperature superconductor to levitate stuff. And as you already can guess from what I'm going to talk about, this is just a piece of carbon and it nicely levitates. So I will get to at some point on why it levitates. Just need to switch the presentation. So I'll get to the point for why it levitates, this piece of carbon. But in general, I was asked then to give a talk not only about this type of carbon, but any type of carbon, because not only does this provide you with some cool quantum mechanical effect of actually levitating shit, it also, carbon is kind of an interesting material in the fact that you guys are yourself mostly made out of carbon, right? So it's a very common element, and for me it connects this idea of quantum matter physics that we do really cool quantum mechanical stuff on things that are very basic and very much in your life. You don't need to dig tunnels under Swiss mountains, you don't need to have like a fancy lab, it's something that I can here have on my tabletop and that already shows effects that are truly quantum in nature. In short, when you, for example, read Feynman lectures, Feynman, this handsome guy over there, he said, well, quantum mechanics is a description of everything that happens on the atomic scale. Now, Feynman, of course, is always right, and quantum mechanics was originally designed as people really thinking about things happening on an atomic scale, but everything around us is then determined by what happens at the atomic scale and the combination of these many, many, many atoms together. So far, the quantum club was dealing mostly with, indeed, this atomic scale type of quantum physics, like non-locality, qubits, and that kind of stuff. But I hope to convince you tonight that the quantum mechanics of big stuff the size of you and me, is actually equally cool. So when I say big quantum mechanics, what do I mean? Well, Ivo already gave you an introduction on basic electronic properties, but it always boils down to basically three properties. Electric properties, what is the type of, can you get currents passing through it? Magnetic properties, that is also obvious if you ever play with these little toy trains with magnets at the end, or you have a fridge. And the combination is, of course, the interaction between matter and electromagnetic waves, which is known as light, and the interaction that is basically how color is generated. So one of the things that a quantum matter physicist can do is literally calculate the color of some interesting material. But that only works because you don't have a single atom, you have basically infinitely many atoms. So when I say many, what do I mean by that? Well, let's just give a back of the envelope calculation. The typical distance between atoms is measured on the order of angstrom, and angstrom is a kind of wacko unit that's only introduced because it gives you a typical distance of atoms. It's 10 to the minus 10 meters. So if you then say, oh, an atom contains, handful of electrons, the typical density of atoms or the typical density of electrons is about 10 to the 28 per cubic meter. So that's a lot of electrons. You probably recognize that it's somewhat in the order of the number of Avogadro. As Ivo said, there's Pauli exclusion, so you will have, in general, the momentum states. Each momentum state can only contain 2 electrons, actually, because there is spin degeneracy. So each momentum state contains 2 electrons. So they will fill up all the lowest momentum states up to this Fermi, in this case, Fermi momentum, that then also defines the Fermi energy. The relationship between the density is just integrating over all possible momentum states, just a spherical integral, gives you this, something that depends on the Fermi momentum to the power 3. And just to give you an idea of what then the corresponding Fermi energy is, which is just k squared over 2m, this energy momentum relation, you plug in this guy, you get this number, you plug in this 10 to the 28, the reduced Planck's constant is 10 to the minus 34, mass of an electron is about 10 to the minus 31, all in SI units. So if you combine that, you end up with about 10 to the minus 19 joule. And because 10 to the minus 19 joule is a very common amount of energy that you find in quantum mechanics, we convert it into something called electron volts, which is basically 1 electron volt is 1.6 times 10 to the minus 19 joule. So the energy you'll get is roughly on the order of a couple of electron volts. If you convert that into temperature, that's like 10, 20, 30,000 Kelvin, which means that for all practical purposes, even though I feel kind of warm in this room, from the perspective of many-body quantum physics, we are all extremely cold matter. That's maybe why you've heard the term low-energy physics as opposed to high-energy physics. So high-energy physics are people indeed under the mountains shooting their protons against each other. This is dealing with so many particles that effectively we're still at 0 temperature. So, knowing that we're at 0 temperature, we define something like a Fermi energy and Ivo's introduction on band structure. Let's talk about carbon. So, all matter that we know on this planet, at least, is made out of elements of atoms. And all the atoms are nicely arranged in the periodic table, and carbon is number 6, meaning it has 6 protons in its nuclei and 6 electrons on the outside. And even though we are mostly made out of carbon, I learned when researching this carbon is actually not that common on this planet. It's only like 0.003% of our Earth crust is made of carbon. So silicon is much more common in our planet. That's actually the most common element after oxygen and silicon. So carbon is relatively rare, but it plays such an important role in life that we always find it, and we can very easily isolate pure carbon by just taking whatever you find close to you, for example this desk, burn it to the ground, and what left is just pure carbon. So in that sense, it's something that we encounter a lot. Oh, hopefully not burning down the table. Starting from this atom, we can make bigger things. And then really the game is, how can you make bigger things out of simple atoms? It really, really depends, and that's hopefully a take-home message. It really depends on how you put things together. The simplest, nicely non-trivial structure that you can make out of carbon atoms is the so-called benzene ring. You take 6 carbon atoms, and the way that I draw it like this, you have atomic orbitals. I don't know how many of you already did your quantum mechanics course, but there's something called PZ orbitals. These are have a structure that they point up and down with the opposite sign, wave functions of single electrons, and then you can put the 6 carbon atoms in a ring like this. Then you'll notice that you have some excess electrons when you bind these carbon atoms together. So the benzene ring is already your first quantum mechanical object that you can make. It's a superposition of having double carbon bonds here and having double carbon bonds there. The fact that you have these double carbon bonds means that you can glue benzene rings together to make larger and larger structures in whatever you want. And from there on, basically this is still a tiny quantum mechanical object. I can make a big object, namely a whole sheet of benzene rings glued together. And that's what we call graphene. It's a perfectly two-dimensional repeated structure of these 6-fold benzene rings. And this is how it looks like. And I'll get a bit more into the properties later, but for now, one thing that you really should remember, again, we are constructing a material, so it depends where we put the atoms, is that there's 2 inequivalent positions in this repeated pattern. For example, this blue guy, they have always a neighbor in this direction, in this direction, and in this direction. It also has neighbors in the same direction. Whereas the red guys has neighbors in the opposite direction. So that's what we call sublattices. If they have neighbors in opposite directions, and you can split all the atoms. You know, every atom is either a blue, so-called A sublattice, or a red one, a B sublattice. Now this doesn't look very important, but if I want to make a real three-dimensional material, I have to imagine how I'm going to stack these guys, these sheets, on top of each other to make a real three-dimensional material. So this is just a top view with my A and B sublattices. So the simplest thing I can do, I can smack another layer on top of it, just in the same position. This is what we call AA stacking, because the A sublattice of one layer is just on the A sublattice of the other layer. Now it turns out that this is not stable, because you have these PZ orbitals that I mentioned before. They're kind of sticking out. They don't want to be on top of each other. So if I try to do this, what will happen is it will slowly start to slide into a position that's actually stable, the so-called AB stacking, where you have the B sublattice of one layer on top of the A sublattice of the other layer. So that is the stablest configuration that you can make when you have just two layers of graphene. But I promised I will go into 3 dimensions. So how do we do that? You quickly realize that there's actually 2 ways that you can continue this stacking. The first is the so-called ABA stacking. So I have the first layer, the second layer. Now the third layer I put basically in exactly the same position as the first layer. So this looks a bit like this. If you look at it from the side, so the top layer and the bottom layer are exactly at the same position. So I can continue that stacking and make a 3-dimensional material. So I'll call that ABA stacking carbon. The other way is kind of, you notice that there was a shift. I can continue that shift. And that gives you that here it is the bottom layer, and the next layer is shifted, and the next layer is shifted again. So you notice that the third layer is now again above the different sublattice of the first layer. So that's why this is called ABC stacking, and there was no C sublattice, but it's just to distinguish it from the A sublattice. So I can do like stack like this, or I can stack like this. Just the side view again, right? And that is basically the difference between graphite, which you can find in pencils, and diamonds, which you can find in jewelry. That's really it. And it's kind of funny that the only way that I changed is how I put carbon atoms next to each other and either have this ugly gray lump of coal or a beautiful shiny diamond. And that's really, I hope that you're also as amazed as me, that the only way, you only just put the carbons in a different place and you have something that's fundamentally different. So that was about my introduction, and then the rest I'll tell you some of the cool things that you can do with diamonds, with graphite, and with some new stuff that I'm personally also working on. Are there some questions about it so far? That's clear. So let's start with diamonds, because that's the most fancy and expensive one. I'm just going to follow basically what Ivo was doing, namely we have to talk about band structures because that determines the electronic properties and therefore also determines how it looks like. So first thing that you can do, the moment I do this ABC stacking, I can rotate it 45 degrees and I notice that it will actually become a cubic system. So the periodic arrangement of carbons is perfectly the same in all 3 directions. It just repeats this original unit cell, which is actually exactly the same structure as silicon. Only silicon is much more boring and ugly than diamond. So it's this so-called face-centered cubic lattice, which means it's a cube, and on every face, like every side of the cube, there's also in the center another carbon atom. That's just the name. Ivo discussed how does then look like in momentum space. There's all these possible momenta and high symmetry points, and he discussed how you can go from different momentum points, and this is a band structure along these different high symmetry points. And as you notice, it looks very similar to the silicon case. It just had some tiny differences, but you have, as before, the state where you have, at 0 temperatures, these will all be occupied. You have the Fermi energy that happens here. There's a gap where there's no electronic states, and then unoccupied states. So the fact that you have a gap, which is at its lowest value of 4.7 EV, that is already an indication that it's insulating, just like silicon. But it's already a much larger band gap. For silicon it was, do you remember? I don't don't remember the exact number, like 1.82 electron volt. It's more than twice the gap. Yeah, it's more than twice the gap that you'll have in silicon. Now, one of the things that Ivo mentioned but didn't get into because I was going to do that is how it then couples to light. Because one of the reasons we care so much about diamonds is that they're beautiful, they're shiny, they're transparent. So why is a diamond transparent? The theoretical way to do this, and I promised Anna to put in some equations, so here we go. It has to do with a concept which is called the optical conductivity. Because what is light? It's an electromagnetic wave, and conductivity is the property of how a material responds to an applied electric field. This is another way that I formulate just Ohm's law, which I hope you learned in high school. It just tells you the current is proportional to the conductivity and the applied electric field. Now, of course, I'm mostly interested in an oscillating electric field, so that's where this frequency omega comes in. And the word optical refers to I'm interested in this conductivity when this frequency is non-zero. This is opposed to sometimes called the DC conductivity, where I'm looking at the zero frequency one. But now I want this frequency really to be non-zero to tell me the response of light going into this material. Often the response to light is also expressed in terms of the so-called dielectric function, which is just a rewrite of this optical conductivity. And it's a nice rewrite because now you can directly relate this to a concept from quantum mechanical Feynman diagrams called the polarization. So the dielectric function is this relation with the optical conductivity, and it happens to be 1 minus the Coulomb interaction, which is the interaction between electric charges, and the polarization. Polarization is given by this expression in the simplest approximation. And in terms of Feynman diagram, what we should imagine is the light comes in, then it excites an electron hole pair. The electron hole pair later are absorbed, and the light continues. Therefore, this changes effectively the way how light behaves in this material by exciting and absorbing electron hole pairs. Now, how do you excite an electron hole pair? What you need to have a place that's occupied, so I can create a hole there. I need a place that's empty, so I can create an electron there. So that's visualized by this nice arrow, and then the energy associated with that is just the energy between these different bands. So this is expressed in this expression. You have the occupation of occupied states, making sure that the state at the other momentum is unoccupied, and they should have an energy difference omega. Now this expression is in general a complex function, and the imaginary part corresponds to the absorption. It really, light comes in and it creates an electron hole pair, and it doesn't come back out. So how does it look like for a diamond? So these black lines are the dielectric functions. So this is the middle line here. Epsilon 1 is usually referred to the real part of the dielectric function, but let's first look at the imaginary part, which, as I mentioned, gives you the absorption of light. So they didn't bother to draw it, but this epsilon 2, the imaginary part of the dielectric function, is 0 up to about 6.5 electron volt. Now this 6.5 electron volt, you already saw in this diagram. This is the lowest straight up excitation that you get in this bandgap. And it just means that diamonds cannot absorb any light with an energy less than 6.5 electron volt. Just as a reminder, light, the visible light as we know it, has an energy range between 1.5 and 3 electron volt. So it means that any visible light that we can see with our own eyes cannot be absorbed by a diamond. As a result, it's transparent. So it's a very simple calculation. On the other hand, diamonds are also wanted because they're super shiny. Whenever you look at them, you see all these different facets. I'm sorry I didn't bring a diamond that big because that's a bit too expensive, but I just got a picture there, right? This is how you imagine a diamond, all these fancy colors. You see all these like little rainbows everywhere happening. And you know that rainbows happen if you have diffraction of light. And diffraction of light happens because the speed of light for red is different than the speed of light for violet. Right? Then you can have this so-called dispersion, the difference between refractive index between red and violet. It turns out that the real part of this dielectric function literally directly gives you the refractive index of a diamond. Now let's look at that curve. We have here this epsilon2. Now this is the epsilon1, which shoots up here exactly where this epsilon2 begins. And that's actually a property of the dielectric function known as causality. Causality is another word for shit happens after you do it. And that is a very important physical constraint on when you make theories. What that also means is that properties like these response functions, as you call them, the imaginary part and the real part are related by so-called Kramers-Kronig relations. If you then have a jump in your epsilon2, like if the imaginary part is 0 and then suddenly starts, that means that there must be in the real part a divergence at that point. So you see it here. This guy goes as 1 over omega, well, 1 over omega minus 6.5. So around 6.5, this guy shoots up, because this guy starts discontinuously. And because that's relatively close in energy to the energy of visible light, the real part of the refractive, or the refractive index changes drastically in the region where you have visible light. And that's why a diamond is so shiny. So probably the most perfect diamond would be, or the most perfect jewel, I would say, would be a material where you have a gap that's just above, like above here, so you have like intense dispersion and always like rainbow colors shooting from it. Now, when you think of diamonds, there's probably also you think of colored ones. So there's a lot of colors if you go to a diamond shop, not only the white transparent ones, but you have blue, green, orange, red. The interesting thing about that is that the colors in diamond are caused by what's called defects. So everything I said up to now was a property of a diamond when all the carbon atoms are perfectly arranged. But you can have carbon atoms in the wrong place. You can have every now and then a missing carbon atom. This is known as a vacancy. And you can also have sometimes chemical impurities, so that there's not a carbon but some other element. So one of the most famous defects that can occur in diamonds is the so-called nitrogen vacancy defect, where you remove one carbon atom and replace it by a nitrogen, and next to it you don't have a carbon at all, an empty place, a vacancy. This has a very funny property because it absorbs light at a certain, this defect, it absorbs green light, but then after it absorbs green light, it can emit red light. Apart from that it's a funny optical property, this is one of the main reasons why people are using diamonds in laboratories these days, because these NV centers can be the perfect tools for making qubits and therefore making quantum computers. The reason is I mentioned before, you can absorb green light or emit red light. These are the energy levels in this NV center which are created in the otherwise empty electronic region, like in the gap. So you have no problem with all these, you're just perfectly in an insulating region. These are localized states at the NV center. And by tuning an electric field, you can create a sort of resonance between these low states and create a qubit, a perfect state that can be up or down, that can be tuned by electromagnetic radiation and the magnetic field. So this qubit has been proposed as building block for different types of microscopy measurements. It is a perfect single photon source because it can have just one decay, emits exactly one photon when you excite an NV center and then it decays. And because it can create a qubit, this is used to create quantum computers. So you just take a bunch of diamonds, you find all your NV centers, put them all next to each other, and then you can build a quantum computer. You have questions about diamonds? Because I want to, yes?
I have a question to that. Is it, why can it absorb green light and emit red light? Is it like a fluorescence kind of thing? Or what
Yeah,
is this?
it's fluorescence.
I also have one question. Is there any temperature dependence?
That's a good question. I don't know. Probably usually the coherence of your light that you emit is better at low temperatures. That's why you probably want to do.
And energy levels, they're always the same.
Principally, yeah, I think so. But yeah, temperature and interactions could influence that, but I'm not an expert on NV centers. It's just that talking about something mundane as diamonds, and I just want to tell you guys that diamonds are also cool in the sense that you can do quantum computation with it, which is the topics of the previous few quantum class. So, there's no questions, I'm going to switch to the boring cousin of diamond, namely graphite. And here I can do the same thing. When you stack this back and forth, you don't get this cubic structure, you get something which is called a hexagonal structure. This should not be FCC, this should be hexagonal. The Brillouin zone has then different high symmetry points, so this graph looks a bit different, but most importantly, there's no gap between occupied and unoccupied states. And if there's no gap between occupied and unoccupied states, it means any energy I can go here, arbitrarily close, and have tiny energies that I can excite from here an electron to create an electron hole pair. So in terms of the dielectric function, the black one is the absorption. It is pretty high in the visible regime. So this is exactly what you expect from this piece of carbon, that it absorbs light, it absorbs visible light, because there's no gap. The argument is very simple. Now, I promised you to tell you why it levitates, and that's actually a kind of funny property of this guy. When you have here so-called band touching, you have this quadratic, it looks here quadratic, there's a whole band, and the other band exactly touches it. When I now put a magnetic field on that guy, you will create, out of this band touching, you will create so-called lambda levels. Those are basically the quantum mechanical version of these orbits that you have. If you have a charged particle in a magnetic field, the Lorentz force will cause it to have nice circular motion. And this is the quantized version of that. So you have only exact energies available where these orbits, or where these electrons can move around quantum mechanically. The energy of the lambda levels is given by something called the cyclotron frequency. Now, before I had a continuous band, but now I have these discrete energy levels only available. The moment I put on a magnetic field, therefore, all the energy that I had in this window is kind of compressed into this. That means also the energy states that are below here are suddenly increasing in energy. So the energy that you can calculate is this guy, then going from the first lambda level, or the -1 lambda level, to the +1 lambda level. The total energy of these states depends on the magnetic field, depending on how much it's kind of squeezed to the center lambda level. Because then the magnetic field, because then the application of the magnetic field increases the energy of these electrons, they want to oppose that. And the so-called magnetic susceptibility, which is just how this energy changes with the magnetic field, and then make sure that it's dimensionless, is actually negative. So graphite has, of all the materials that we, like all the normal materials that we know, has a very strong tendency that whenever you apply a magnetic field, it creates itself an opposite magnetic field. And that's what this negative or diamagnetic susceptibility means. And here I just have an arrangement of normal magnets arranged in north and south pole orientation. So there's like a little saddle point, and the graphite here pushes itself up by creating its opposite magnetic field of what it's feeling there. So this diamagnetism, as it's called, causes levitation. Now, why are people obsessed about superconductors? Turns out that superconductors are so-called perfect diamagnets. The amount of magnetic field that a superconductor creates is exactly equal to the amount of external magnetic field that you put on. So that's an order of 1,000 times stronger than graphite, but still, if you have strong enough magnets, you can levitate graphite. In fact, you are diamagnetic, so if you have a strong enough magnet, you can just be levitated. And this is not a joke, because famous André Geim, the guy who actually discovered graphene, once levitated a frog, just to show that organic matter is diamagnetic. So one of the things that we actually use graphite the most for is that it's flaky. In other words, when you use a pencil, that you literally use the fact that when I touch graphite, it just pieces of it fall off all the time. And that is because when you make these layered structures, unlike the diamond, which then had in total the structure was the same in all directions, here there's really a difference between in plane or out of plane. And in fact, between the layers, there's no covalent bonding. There's no electrons shared between those layers. They're only stuck together by something called the van der Waals force. And that is a very weak force in global scales. So when you move a pencil, what you do is constantly like shifting off these layers of graphene out of your graphite. And to end this, I have one funny feature of this graphite flakes or graphene is just look at the band structure again. Now, the band structure of a single layer, graphene, has a funny property. Just like graphite, it is gapless. The bands touch here, but it's no longer quadratic touching, it's this linear touching. This is something which we call a Dirac cone. The reason why we call it a Dirac cone is that in this case it can be described by this Hamiltonian, where you have sigma is a Pauli matrix that refers to the sublattices of this graphene. So remember the A and B sublattices? K and Kx and Ky are the in-plane X and Y component of the momentum. This equation is literally the equation that Dirac wrote down when he was trying to develop quantum electrodynamics. The only difference is Dirac wrote it down in 3+1 dimensions. This is a 2-dimensional version. But it literally then describes what we call relativistic, because that's what Dirac tried to do. He tried to make a relativistic quantum theory. It has the same property as relativistic massless fermions. And because it has relativistic properties, you can do all kinds of cool relativistic effects in graphene. I'm just going to name one, which is called Klein tunneling. The idea is, imagine I have my sheet of graphene, now I look from the top and I put a potential barrier on it. Now you remember from quantum mechanics, if there's a potential barrier, there's always a chance that you'll tunnel through. And that probability usually decreases the bigger you make your potential, right? But now, if I have an ingoing wave with a certain momentum, it has this two sublattice structure, and the relative phases between the two sublattice structures, like it's what we call a spinor, are determined by the direction. That's the property of this Dirac cone. Now, if I ask, okay, there's a certain probability that it will be reflected, right? And there's a certain probability that it go through, and it doesn't matter which one you calculate, but just calculate the one that's reflected. As a function of this angle, this reflection is also, that state is determined by the shape of this relativistic Dirac Hamiltonian. So if you want to ask what's the probability that I come in here and then scatter here, I just take the in state, the potential, and then the out state. So I plug in these values, and then you'll find out that it's dependent on the sign of the theta. In other words, if I perfectly come like this with zero angle to it, there's zero probability that I'm reflected. So no matter the height of my potential, I will always go through. So this is a very funny relativistic effect that it's called Klein tunneling after the guy who first came up with it, that relativistic massless particles can tunnel through any barrier no matter how high, and in fact they will tunnel with probability 1 through that barrier. Now when people realized that graphene, which was first isolated and used in experiments about 15, 20 years ago, they quickly realized, oh cool, we can try this Klein tunneling. So they made like a graphene sample, they put like a top gate on top of it that would represent this barrier, and then they needed to do some math to make sure that they would only have electrons going perpendicular to this barrier, and they really could see that, this is a paper from Andrea Young for 2009, that graphene perfectly behaves like this relativistic perfect Klein tunneling, ignoring all kind of potential barriers. So, in the beginning of the talk, I mentioned that one of the take-home messages is that whenever you stack the carbon in a different way, it has completely different properties. Now we have diamond and we have graphite, and I just want to end the last two slides with something that I've been looking at, namely twisted bilayer graphene. You can take two layers of graphene and stack them on top. This is actually two layers in the AA stacking, but you're not limited to doing this AA or AB stacking. You can also do it with any kind of rotation. So why would you do this? Well, it was proposed about 10 years ago that if you take two of the layers and you twist them, you have two of these Dirac cones with these interesting relativistic properties. The moment you put them close to each other in momentum space, they start to, the crossing that you have starts to become an anti-crossing, and then depending on the twist angle, you can actually get a place where you have exactly flat electronic bands. And since flat bands represent the kinetic energy of particles, the moment you have flat bands, you are completely dominated by interactions. And that's actually a regime that we do not understand yet, that goes beyond band theory. Things will start to happen that we cannot describe with just band theory. So everything that Ivo said, that's already known, that's the stuff that we teach, but everything that we do not understand is when we can throw the band theory out of the window and we need to come up with new things. So one of the two things that I can mention that have been observed in this case, well, the first is superconductivity. It's the property that you can get current through without resistance. And only, well, 5 years now ago, it was for the first time realized in just a material that's purely made out of carbon, namely twisted bilayer graphene at a very specific 1.1 degree twist angle, or sorry, 1.05 degree twist angle. Another cool aspect that's been observed in twisted bilayer graphene is something called the quantum anomalous Hall effect, which is a property that even though it's an insulator, it has perfectly quantized currents running along the edge. So currents running along the edge can be quantified by something called the transverse resistance, or the XY or Hall resistance. So there's exactly just a combination of fundamental constants, h divided by e squared, amount of current going along the edge of this system. And most of these things are really active fields of research. We don't know what causes superconductivity in twisted bilayer graphene. Turns out that explaining currents along the edge is actually a lot simpler, and if you want during the apéro I can tell you a bit more about the research that we've been doing in that direction. But for now, I hope I can give you the take-home message that depending on how you stack carbon, you can get completely wildly different things. We talked about the main difference, graphite, diamond, is ABA or ABC. Different band structure, different magnetic and optical properties. In the case of graphite, we have the cool property that monolayer graphene can have relativistic effects and interesting future interaction effects in twisted bilayer graphene, and diamond is actively used for quantum computing and quantum circuitry. So with that, I'll thank you for your attention.
Now we have some time for the questions. So do you have any questions? Okay, maybe I can start with the last time and then there will be more. So about the last picture and the superconductivity. So are there any research which show how the area of superconducting state depend on the angle, the twist angle?
Yeah, it's roughly you said area, like one thing that we can do is the TC, which is the maximum thing, and it looks like this, where the height is around roughly 1.1 degree, which is therefore called the magic angle of twisted bilayer. But it's highly sample dependent, and there's many groups with different properties, and how you make it and what the weather is at the day depends on exactly what you see.
And how wide is this area?
Oh, it's very small. This is like 1 and this is 1.2.
Okay.
Yeah, so you need also very high quality machinery to make it exactly 1.1 degree, which actually is done in the gap. So maybe you can, you know, the Ancien École de Médecine, they have like machines that they can make this 1.1 degree. The one building on the corner next to the bridge, there, they do this kind of stuff.
But it should be periodic, right?
Should be periodic. In the angle?
Yeah.
No. This
Well,
goes
it's 31
to 0, nothing happens, and then to
30, right?
to 30.
Yes.
Yeah, sure. But no superconductivity. Yes, superconductivity.
Yeah, okay.
No superconductivity.
Yeah. More questions? Then I guess if you think that you still have questions, you can ask them on the apéro.
Yeah, check out the superconductor.
Yeah. And let's then look again at Ivo. And now a small announcement. From this week we have our YouTube channel, and all of the previous videos, they're also there, and I'll send the link tonight. And if you're interested in watching previous talks and this talk as well, you are very welcome to our YouTube channel.